Alrighty, good morning, everyone. So, quick recap what we did last time. At the very end, anyways, we start talking about the power loss. So again, as the charge carriers start going into the resistor elements, it starts making those head-on collisions, which then causes these guys to oscillate more and more and more violently, which then causes their kinetic energy to increase, causing their temperature to increase, which then causes a loss of energy to the rest of the world. So as we said last time, this power loss then is simply equal to the power which is being delivered by conservation of energy, which we then found that the power delivered, which is equal to the power loss, is equal to the current times the potential difference across that electrical element. That's for any electrical element. Or using Ohm's law, that's also equal to the current squared times the resistance, or the potential squared divided by the resistance for resistors only. So I have to have some sort of resistor for these statements to actually make sense. But again, that top one works for any case. So it could be a resistor, it could be a capacitor, it could be whatever. Could be a battery, etc. So great. So let's do one more example of this. Now we're going to move on to bigger and greater things. So this says we have the current density magnitude in a certain circular wire is J is equal to A. So in hindsight, I probably should have called that something else like C, but whatever. A is simply a constant times then the distance squared you are away from the center axis of the wire, where A is just some number. This is 2.75 times 10 to the 10th amps per meter to the 4th in a wire which has a radius of 3 millimeters. So in this case, what we want to do is there's potential difference applied from end to end across this blue wire, which has a potential difference of 60 volts. And again, what we want to know is how much energy is converted to thermal energy in 1 hour worth of time. So here I want to know eventually what's the amount of energy which is being lost. So let's draw our picture. So here's my wire, right? Here's my wire. This thing has a radius of r, so there's my radius of r. We're going to apply some sort of potential difference across here. So here's my potential difference. V, where the potential difference then is equal to 60 volts. My radius was equal to 3 millimeters. And we're told that the current density flowing through this object, so in this case, my current density is going to go this way. J as a magnitude is equal to some constant A times R squared. So what? So from here, all I really want to know then is what is the energy lost? So in this case, what is my energy lost in the time frame of 1 hour? So this is my delta T. So my delta T in this case is 1 hour. So how much energy am I going to lose from this particular wire in an hour if I'm running 60 volts over that? Feels okay? So first things first, let's talk about energy. So remember that power is equal to the time rate of change of energy, which means if I want to know the amount of energy which is actually being lost, in a general sense, my power is going to be time dependent, which means I would have to actually do an integral. So from here, if I want to know the amount of energy, I would then say, well, my du is equal to PdT, which means I then integrate both sides, integrate this from the initial amount of energy, which is 0, to the final amount of energy. And I'm going to integrate this from the initial amount of time to the final amount of time. So this just says that my energy then is going to be equal to the integral of the power integrated over the time from the initial time to the final time. So what's power? So again, power, we know is simply going to be what? So our power, in this case, is the power loss, which is then going to be equal to any one of those three things. So it's going to be this guy, or this guy, or this guy, depending on, again, what it is that I need. Now, in this case, I know the current density, which means I can find the current. I also know the potential across the wire, which means I know V, so we're simply going to use the first one. Right? So in this case, I'm going to rewrite this then as the integral from 0 to T of the current times the potential integrated over time. So the only thing I need to find out here then is what is the current? Well, again, we know the current is related to the current density by the integral of the current density integrated over the cross-sectional area. So let's do that integral first. So here we know that the current then is going to be equal to the integral current density dotted by the differential area, whereas we told before the differential area then is going to be equal to 2 pi r dr. So we're dealing with a cylinder in the r hat direction. And again, since j also points in the r hat direction, this is going to be equal to the integral of j essentially times 2 pi r dr. So this is something we wrote down before. Now in our case, we know that j is equal to what? Some constant a times r squared. So I'm going to rewrite this then as what? 2 pi times a integral. I'm going to get an r squared times r dr. And I'm going to integrate this over the cross-sectional area of the wire. So I'm going to integrate it from 0 out to the radius of the wire. So this is my radius. So then we'll go back here. Call that capital R instead of little r. And so we have the right notations here. Okay. What's r squared times r? R cubed, good. And if I integrate r cubed dr, what do I get?
R to the fourth.
Good. So this is going to become 2 pi a capital R to the fourth all divided by 4. Or that 2 is going to cancel with the 4, so it's going to become pi a r to the fourth all divided by 2. So this is my current. Now let's put our current back into our previous expression, which was this guy. So now we know what the current is, so let's plug it into here. So finally, this then tells me that my energy, which is being lost, is going to be equal then to, so in this case, we have the current, then going to be pi a r to the fourth divided by 2 integral from 0 to t of the potential dt. Now, in this expression, pi a r to the fourth times v divided by 2 is anything in that expression time dependent. Meaning, is the radius of this thing change over time? Is the potential change over time? Is pi change over time? Is a change over time? Is anything here time dependent? No. So all this stuff is actually just equal to a constant. So that all comes outside the integral. This becomes pi a r to the fourth divided by 2 times v integral dt from 0 to t. What's the integral of dt? T, if I go from 0 to t, so this is just simply t, or the same thing we call delta t. So it's going to be then pi times a times r to the fourth times v, all divided by 2, all times delta t. For here, we did not put in our numbers, so it's going to be then pi times a, which was 2.75, times 10 to the 10th, times the radius, which was 0.03 meters to the fourth power, times the potential, which was 60, times our time, which is 1 hour. So how many seconds are in 1 hour? 60 times 60. Good. So that's 3,600. All divided by 2. Look at my numbers. What I find in this case then is over the time span of an hour, we're losing 7.56 times 10 to the 5th joules. So this is the energy which is being lost. So 7.56 times 10 to the 5th. That's a decent amount of energy. Also 1 hour time span. Okay. What's up, Omar?
No problem again.
The problem? Sure.
Which equation do we use to get our rule from?
Which one?
The power one.
Oh, the power one. So I'm just saying, in general, remember that power is the time rate of change of the energy.
Okay.
Now, in this case, it turned out that the energy was actually time independent, which means that this is the same thing as the change in energy over change in time. But again, I want to do it more on general, just in case. Okay. Just to remind us of these things. Doesn't mean it's always time independent. Okay. So that's it. We're done with this chapter. Life is great. So I got a couple group assignments for you, but I'm gonna push those off. I'm gonna start the next chapter, and then with about 20 minutes left, Ruth, you're in charge. So 20 minutes stop. I give you some time to work on those. So we're gonna start the next chapter for the next 20 minutes. Okay? So we're gonna start the last chapter for this upcoming exam, which is then chapter 28. We'll talk about chapter 28. So chapter 28, we're going to start off very similar to what we did with capacitors, and then note that again, I only manufacture a certain amount of resistors, just like I manufacture only a certain number of capacitors, because again, oops, I'm pen at myself. Manufacturing speaking, and again, money-wise, monetary speaking, it's not a good idea to basically make any type of resistor anybody's ever going to need, because all you're going to end up doing is basically wasting money. You're going to have to make basically an infinite number of different resistors, which means you're going to spend an infinite number of money to basically build those resistors and hope you get a fraction of that back. Right? So what makes more sense is to make a few standard different types of resistors and then make other people create the type of resistors that they want from those pre-existing resistors. Which means we're going to add resistors in parallel and series, just like we did with capacitors, adding them in parallel and series. And what does that do to the overall resistances? So basically, we're going to go back to parallel and series. This time we're going to look at resistors instead of capacitors. So good. So let's remind ourselves what series is. So in this case, here's my battery. I'm going to connect that to 3 resistors. Remember, when we draw resistors, these are simply squiggly lines. So it's my resistor R1, R2, R3. This is my battery. So I'm going to call that my EMF for now. And again, this guy is in series. Same thing, put a battery here. I'm going to connect that then to these guys. So here's one resistor. Here's my second resistor. Here's my third resistor. So here's my EMF. This is resistor R1, R2, and R3. And this is what we call parallel. And as a side note, for all of you who have lab today, this is what we're doing in lab today. You're going to measure these things. Good. So let's talk about series first. So what has to be true is whatever charge comes out of the battery has to be the same amount of charge which goes through this resistor, which has to be the same amount of charge which goes through this resistor, which has to be the same amount of charge which goes through this resistor by conservation of charge. Which basically means that the rate at which the charge goes through this resistor has to be the same as the rate at which they go through this resistor, which means they have to be the same as the rate that goes through this resistor, which means the currents are all the same. That's all this thing says. So that means whatever current comes out of the battery is the same current which goes through this resistor, is the same current which goes through this resistor, and it's the same current which goes through this resistor. So in series, what has to be true is that all the currents are going to be the same. But since the currents are all the same, but in general all the resistances are different, that means then all the potential drops across each one of these guys is also going to be different. Which means I'm going to have a different potential drop here than I have for here, which I have for here. But by conservation of energy, what has to be true is that drop across here plus the drop across here plus the drop across here has to be equal to the amount which is supplied by the battery. This has to be true. Okay with this? Good. Now, let's look at this one. In this one, whatever current comes out through here, it's going to come to this point, which again is our junction. Remember, at a junction, charge, i.e. current, can split and go in different directions depending on the size of the resistors. Ohm's law tells us that if I want more current, I have to have a smaller resistor. Because Ohm's law says that for a fixed amount of potential, the current times the resistor is equal to that fixed amount of potential, which means for the smaller amount of resistance, the greater amount of current which is flowing through each one. Or again, if you want to think about this as hoses, the bigger the hoses, the more current I'm going to have going through it as opposed to a smaller amount of hose, which means I have less water. Or if you want to think about this in terms of your heart, this is also true about your blood vessels. So whatever blood goes through whichever artery is going to depend on the cross-sectional area of that artery, i.e. less resistance, you can have more current going through it, which is why cholesterol is bad. Cholesterol clogs up your arteries, less blood flows through, we got problems. Right? Whatever you want to think about this, however you want to think about it, All this says then is whatever direction the current goes through, it's going to go through the path of least resistance. So the one which has the least amount of resistance is going to have the most amount of current running through it. But as we said before, what has to be true in this case is that the current comes in, if I go through this portion here, back to the battery, that means this potential here has to be the same as that on the battery. Or I can go through the center one, which means that this potential here has to also be the same as that for the battery. Or I can go through this closed loop, which means that the potential here also has to be the same as that of the battery. So in in parallel, potential has to be the same as it was before. So it has to be the same here is potential. Which means the potential here is the same as the potential here, which is the same as the potential here. However, since all the resistances are again in general different, that means all the currents going through each one of these is going to be different. So in here, I'm going to have one current here, I1 going through this guy, current here, I2 going through this guy. This one's going to have its own current, it's called the I3 going in this direction. But again, what has to be true is by conservation of charge, whatever charge comes out of the battery has to split up into these three things, but by the time we get back down here, they have to recombine to go back into the battery, which means that it has to equal the same amount of charge which was coming out of the battery or the same amount of current. Which means that the sum of these three currents has to be exactly the same as the sum of whatever current is coming out of the battery itself. So we're going to use these ideas again to basically write down how do we add resistors in series in and how do we add resistors in parallel. So let's go ahead and look at series first. Let's do series first. So again, here our claim is that we can combine all three of these resistors into one single resistor, which is what we call the equivalent resistance, just like the equivalent capacitance. All this stuff is going to get combined down to one battery connected to one resistor. So this is REQ. Same amount. Now again, what has to be true by charge conservation, whatever current comes out of here has to be the same as the current which comes out of here. And again, what has to be true is that the potential here has to be the same as the potential across the battery by our loop rule. Because again, whatever comes out of here has to be dropped by whatever comes through here. So again, here we're just simply going to say then that's what the total potential E must then be equal to the potential drop across this resistor plus the potential drop across this resistor plus the potential drop across this resistor. So I have V1 plus V2 plus V3 has to be equal then to the EMF across the battery. Well, Ohm's law says that what V is equal to the current times the resistance. So I can rewrite this then as the current times resistor 1 plus the current times resistor 2 plus the current times resistor 3, or finally the current times R1 plus R2 plus R3. But again, my conservation of energy, the potential here has to be the same as the potential here, so I can rewrite the potential E as simply whatever current is going into the REQ. So my left-hand side is then simply going to be I times REQ, which means I get I times REQ is then equal to I times R1 plus R2 plus R3. Finally, those two currents are the same, so we can get rid of those currents. And this then, at the end of the day, tells us then that the equivalent resistance is simply then going to be the sum over all the individual resistances. So what I finally get then is that REQ is equal to R1 plus R2 plus R3, or in summation notation, this is then the sum over Ri. So the overall effect then of adding resistors in series is what? Did it increase the overall resistance or decrease the overall resistance? Increased it, right? So this increases the overall resistance. So adding them in series increases the overall resistance. Unlike with capacitors, when we added them in series, we had to inversely add them together, which overall decreased the amount of capacitance. Over resistors, it does the opposite, it increases. Why does it do that? Well, the same reason that we talked about with capacitors is it effectively increases the length of the resistors. Again, if I go back to my picture, each one of these guys has a certain length to it. So if I add them all next to each other, all that effectively does is increase the length. And remember for resistivity, that resistance is equal to resistivity times length divided by the cross-sectional area. So if I increase the length, I increase the resistance. So effectively what I'm doing here is increasing the length, which overall increases the resistance. It was okay? Not too bad. Okay, I'm gonna write this down here. And when we had capacitors, we had 1 over CEQ was equal to the sum over I of 1 over CI in series as well. So these guys are opposite from each other. Next, let's go ahead and look at parallel. Let's do parallel. So again, parallel, here's my battery. I'm going to combine that then with 3 resistors, R1, R2, and R3. Again, our claim is that we can combine all these down together to form one equivalent resistor. This is going to be my REQ. Now here what's going to be true is that the current which comes out of here, I, has to then be the same current which comes out of here, I. But in this case, it's going to split to I1 here, I2 here, and then I3 here. But as we said in the beginning, what has to be true is that the potential across each one of these has to be identically the same, which is going to be the same as that of the battery. But the sum of these 3 currents have to recombine down here to equal that which is coming back into the battery. So those 3 currents have to add whatever comes out of the battery itself. So in this case, we have to have that the current I must be equal to I1 plus then I2 plus then I3. Now again, Ohm's law tells us the potential is equal to the current times the resistance, which means the current then is equal to the potential divided by the resistance. So the right hand side I'm going to write as the EMF divided by R1 plus the EMF divided by R2 plus the EMF divided by R3. But again, conservation of energy tells me that this potential here has to be the same as this potential here. So rewriting in terms of him, I have then the current with that resistance going in. So I can rewrite the current then as simply my EMF divided by RE. Finally, the same potentials. So I can delete all those potentials there, which then tells me that 1 over REQ is then equal to 1 over R1 plus 1 over R2 plus 1 over R3, which then tells me that 1 over REQ is then equal to the sum over I of 1 over R. So in this case, resistors in parallel, I then add them inversely. Unlike capacitors, when I have capacitors in parallel, I added them directly. Right? What does this have to the overall effect of the resistance? Decreases the effect. So this decreases R. Again, why does it decrease R? Well, again, if I go back to my picture, imagine if I squished all these guys together, what I'm doing is I'm increasing the overall cross-sectional area. So in this case, I'm increasing the cross-sectional area. But since resistance depends inversely on cross-sectional area, so if I increase the cross-sectional area, I decrease the overall resistance. So this is my physical effect of doing all that. So I'm doing this by increasing the area. Increase the area, I decrease the overall resistance. Now again, just to remind ourselves, when we had capacitors, we had CEQ then was equal to the sum over CI, again, when these guys were in parallel, which again means that these guys are opposite from each other. So I do the opposite effect. Okay. That's it. So ultimately, all you need to know is one set, and you automatically know the other set because it's the opposite of that. Means on your equation card, if you want to write down capacitors, just make a note, resistors are opposite, and you don't have to waste all that room writing it all down. Or you can write it down if you want. Okay. So good. So let's do what we did last time too. Let's simply look at a few examples of this. So look at some examples. so this says in the circuit below, what is the equivalent resistance for these 3 resistors? What are the currents flowing through each one of the resistors, and how much power is delivered by the battery? And then how much power is lost by each individual resistor. So we're going to do a lot of different things here, but basically the idea works exactly the same way as before. So just like we did with capacitors, the first thing we have to do is identify what's in parallel and what's in series, add those together, redraw our pictures every time we add something together to get all the way down to an REQ. From there, find the current, work our way backwards by unraveling what it was that we just did, and then find all the different things that we want along the way. So we're going to do all the same exact stuff as before. So good. So let's draw all of our monstrosity down. So here's our example. There we go. Just right here. So here's my battery. So here's my battery. EMF was equal to 120 volts. Connected then to R1. Then connected to R2 as well as R3. And this thing does R1. Oh, sorry, R2. This is R3. For R1, we know was equal to 400 ohms. R2 was equal to 500 ohms, and then R3 was equal to 700 ohms. And again, what do we want to know? We want to know what is the equivalent resistance. So what is REQ? After our question, we want to know what are the currents flowing through each one of the different resistors. So we want to know what are the different currents. So let's write down each one. So I have an I1 through here. I have an I2 through here. I have an I3 from here. So what I want to know is what is I1 equal to? What is I2 equal to? What is I3 equal to? What else do we want to know? We also want to know how much power is being delivered by the battery. In this case, I want to know what's the power by the battery. And then finally, I want to know what is the power lost from resistor 1, what's the power lost by resistor 2, and what's the power lost by resistor 3. So these are all the beautiful things that we want to know. Was okay? So then, first thing we want to do is identify what's in parallel and series. So what's in parallel, what's in series? Good. Which is then? Good. So let's do all that in steps. So good. So again, let's redraw. Here's my EMF. What we're going to do is combine R2 and R3 together into one equivalent capacitor. So this is my R23 and this is my R1. Beautiful. So next thing, these guys are in series, as Tim told us. So finally, I'm going to write one more. So this is going to be my RE. So first things first is we know R23 came from 2 resistors which were in parallel, and how do I add resistors in parallel? Add them inversely, right? So in this case then I get R23 is then equal to R2 times R3 divided by R2 plus R3. So it's going to be the same thing then as 500 times 700 divided by 500 plus 700 ohms, which works out to be 290 ohms. Finally, REQ came from 2 resistors which were in series, and how do I add in series? Just add them. So I get these guys, right? R1 plus R3. R1 was 400, so this should be 690. I'm happy when I can do basic math. Okay. Okay. So now that we have REQ, we can now find the current which is coming out of the battery. Let's call that current coming out of the battery simply IEQ. So Ohm's law then tells us that IEQ is going to be equal to the potential, which in this case is the EMF, since the EMF here is the same as the EMF here by conservation of energy, divided by a resistance, where a resistance in this case is simply REQ. So it's going to be our potential, which was what, 120 divided by 690, which then works out to be 0.174 amps. So this is my IEQ. Okay? Good, so now we have IEQ, so now we're gonna do is start working backwards. So now we know the current going through here, but we also know that REQ came from two resistors which were in series, and what's the same in series? Current. So what I know then is that the current going through this guy is IEQ. I know the current going through this guy is also IEQ because these guys are in series, which means that, am I going over?
Yeah, 20 minutes to stop.
Just happened. Let's finish this up quick, and then I'll go. Good. So I now know that current I1 is simply equal to IEQ. So let's do that. So from here, what I know is that current I1 is then equal to then IEQ, which is then equal to 0.174 amps. What I also know is that the current I23 is also equal to the current IEQ, which is equal to 0.174 amps. Okay. So now, what I also know is, let's go back, I know R23 came from two resistors which were initially in parallel, but what's the same in parallel? Potential, right? So what I know in this case then is, since I now know IEQ, I know the resistance, I can now find a potential here, V23. But I know since these guys were in parallel, that means the potential here is the same as the potential here, which is the same as that amount of potential V23. Let's do that. So now let's go ahead and find V23. So now I know V23 by Ohm's law is going to be equal to I23 times the resistance R23, but that's the same as IEQ times the resistance R23. So it's going to be then equal to 0.174 amps times 290 ohms, which means my potential, V23, is equal to 50 volts. Okay. Good. So now, since I know the potential across each one of these guys, and I also know the resistance is R2, and I know the resistance R3, I can now finally find I2, and I can find I3. So from here, we can then say, well, my current I2 by Ohm's law then is going to be the potential, which is V23, divided by the resistance of R2. So it's going to be 50 volts divided by 500 ohms, right? So it's going to be 0.1 amps. I3 then is going to be the potential V3, but the potential V3 is simply V23 divided by the resistance R3. So it's going to be then 50 volts divided by 700 ohms, which is then going to be 0.074 amps. Now, as a good check, what we know is that what? This is IEQ, which means the sum of these two currents has to equal that current, which they do in this case, the light is great. So good, so we're almost done. We got two more things to do. So the next thing we need to know is, what's the power delivered by the battery? Well, we know the power delivered by the battery is then going to be equal to, by the first power, this is going to be the current, which is the current coming out of the battery, which is IEQ, times the potential of the battery. So this is my power delivered by the battery. So it's going to be equal to 0.174 times then 120 volts, which works out to be, right down, let's switch to the other thing. So that works out to be 20.819 watts. Okay. For the power lost by resistor 1, we can use the second one, which says we now know the current is I1 times the resistance R1. So using the first one, I'm going to write this as I1 squared times R1. So it's going to be equal to 0.174 squared times the resistance, which was 400. For the second one, using the same expression, I'm going to get an I2 squared times R2. Then going to be 0.1 squared times 500. And finally, for the third one, P3, I3 squared times R3, then going to be 0.074 squared times 700. Plug in all of our numbers, we find finally these expressions. So we get 12.04, 5.121, and then 3.658. And again, just to check, what has to be true then is the power dissipated by resistor 1 plus the power dissipated by resistor 2 plus the power dissipated by resistor 3 has to all equal the power which is being delivered by the battery. So another follow-up check we can do is simply add these three numbers together, and it has to equal that. So great. Parallel incidence. It's okay? Same stuff we did before. So that brings us to, I promise, let's talk about the group assignments. So we got 3 for you today. But it's kind of tough. Okay, 15 minutes. So the first one has 2 on it. So this one says we have potential difference of 1.2 volts applied to a 33-meter length of 18 gauge wire, where 18 gauge means that the diameter is 0.04 inches, which I'll put it into meters. And I want you to calculate a whole slur of different things. So what's the current? What's magnitude of the current density? So it's J. The drift velocity. So relating the drift velocity then to the current density, things that we did last time. D, the magnitude of the electric field within inside of the wire. So that's just looking at the potential divided by the length. So that's nice and easy. Where was I? So, and then finally, the rate at which thermal energy will appear in the wire. So that's the power loss, basically. So this is all looking at power loss. So for this guy, you just need to know what's the resistivity of copper, since we're dealing with copper wire. And then this is the number density. So that's how many copper wire or copper atoms, copper electrons, sorry, per centimeter cubed in this case. So this is kind of a straightforward question, so not too bad. Second one then says we have a steady beam of alpha particles, which has a charge of twice the fundamental charge, traveling with a constant kinetic energy of 20 MeV. So what's an MeV? So an MeV is another unit we can use for joules. Let's work on EV itself. What an EV means literally is it is the energy it takes to accelerate a charged particle of charge E, so fundamental charge, so a proton or electron, through a 1 volt potential. So I'll write that down. So this has to do with potential energy. So an EV is literally equal to the fundamental charge, which is 1.602 times 10 to the minus 19 coulombs times 1 volt. So this is then equal to 1.602 times 10 to the minus 19 joules. So this is an EV. So EV literally means the potential required to accelerate, or sorry, the energy to accelerate this guy through a 1 volt potential. M is mega. So MeV is the same thing as what? 1 times 10 to the 6th EVs. So it's a mega electron volts. So it's just a unit of energy. Okay, so let's go back to our question. So this thing has 20 MeV worth of kinetic energy, and it carries a current of 0.26 microamps. So it says, if the beam is directed perpendicular to a flat surface, how many alpha particles strike that surface in a time frame of 3 seconds? So it's going to draw what's happening here. So let's say, here's my beam of alpha particles. I'm going to shoot that against a flat surface here. And what I want to know then is, within a time frame of 3 seconds, how many alpha particles am I going to have here? So what is the number of alpha here? And delta T equals 3 seconds. So basically, I'm depositing alpha particles onto this thing. So how many alpha particles will I get in 3 seconds? That's part A. Part B then says, at any instant, how many alpha particles are there in a given 20 centimeter length of the beam? So what does that mean? So that means that if I cut out a chunk of the beam, so let's say here's my chunk of the beam I'm going to cut out, where this is has a length which is equal to 20 centimeters. Again, how many alpha particles are inside of here? In that 20 centimeter length. So that's part B. Part C then says, through what potential difference is it necessary to accelerate each alpha particle from rest to bring it to an energy of 20 MeV? So this is just talking about conservation of energy. So we got to go back to what we did on the last exam, but part C wants to know, okay, here's my potential difference. Let's call that simply V. Here's my alpha particle, and I'm going to accelerate that guy through so he comes out with a final kinetic energy, which is equal to 20 MeV. What then is my potential difference to make this happen? So in this case, we're just going to use conservation of energy. We're just going to say that my change in kinetic energy plus my change in potential energy must be equal to 0. Now, the first two parts are basically you're only manipulating the definition of current. Right, so remember, current is simply the change in charge over change in time. But here you're doing it in kind of interesting ways. So using kinematics and using energy and things like this. So this problem, again, pretty straightforward. Let's talk about the last one before I give you some time to work on these. Just real quick. The last one says that we have a light bulb filament, which is made out of tungsten, which has a resistivity of 5.6 times 10 to the minus 8 ohm meters, in the form of a cylinder, which has a radius of 5 times 10 to the minus 5th meters, and has a resistance R, which is equal to 20 ohms, and a length of L to it. So here, this is the resistance. The radius here is little r, right, and has a length of L. This guy's going to be connected to a battery, which is shown here, where that battery has a potential of 120 volts. Good. From here, what you want to do then is determine the length of this tungsten wire. So you're just using the definition of resistance in terms of resistivity. So that's pretty easy. The magnitude of the electric field inside. So again, I know the potential here is the same as the potential here. So I know it's 120 volts. I just found the length. So just take that 120 divided by the length. That's the electric field. The number of electrons per second that pass through the cross-sectional area of the wire. Number of electrons per second is actually just the current divided by the charge of the electron. Number current is the total number of charges per unit second, which means if I want the total number of electrons, I'm just going to take that charge divided by the fundamental charge, giving me the total number of electrons. So that's all that part is asking. Part D then, I want to know what is the power which is being dissipated. So now I know the current. I know the potential, so in this case, I can then find what is the power which is being lost. Or I know the potential, I also know the resistance, so I can use that one as well, which is V squared over R, probably the easier way to actually do it. And then finally, Tim and I know this too well. The rest of you learn this when you get a little bit older, you gotta actually pay for more things. The electric company charges you the privilege of using their electricity. In this case, they're going to charge you 15 cents per kilowatt hour to use your light bulb. Right? A kilowatt hour is a unit of energy. Remember, watts is energy per unit time, which means that a watt hour is the same thing as a unit of energy. So I'm taking a power times the time, which is the same thing as an energy. So what you want to know then is how much money do you have to pay the power company if you left this tungsten wire on, or the light bulb on, for 30 days straight? Would never turn again. How much money would that turn? Now, what I also got inside of this problem is all the connection fees, and utility fees, and privilege fees, and all kinds of other stuff that they charge you. Which means the $7 that you should be spending is actually more like 30 or 40 after they get done charging you for everything. So these are the three problems. They got about 7 minutes. They're kind of talking to each other a little bit about these things. And hopefully Friday will give you some more time to work on these. What's up, Derek? Not on me.
Okay.
Not on me. Send me an email tomorrow night to remind me to bring it over to you. Okay. Wednesday, okay?
Yeah.
If I kept them on my bag, they'd just be a big mess by the end.
Like I'm gonna study, but
You have a version from inches to meters.
I'm sorry,
You have a version from inches to meters.
offhand, no, but that's what you do.
What?
Switch yourself.
I
Guys like using it to watch videos and stuff. Fine. That's something.
I have a question.
Sure.
How did you know Jay was there?
Oh, it was given in. So yeah, so for me to use this, I have to know the functional form of the code. So yeah, so in the problem it was told was that this was the functional form. Yeah. Yeah, if we were given I, we would have to go through this. Yeah. So in that case, we would just jump directly here, and then just work up from there. So then it just depends on the potential or the current we're actually at. But if they're both constant, then it just becomes I times A times delta.
Thank you.
You're welcome.
You must be-
I did this morning. I forgot to email to you though, so.
That's fine, I can check it.
Okay.
I just wasn't sure, so I checked this weekend and I didn't know if you had.
No, I got busy doing 1,000 other things.
Well, that's fine, I just wasn't sure.
My wife made me go back to the backyard on Saturday. I think we're finally done with it now.
I don't know why I'm getting this, just like.
Well, it could be me, so let's find out.
It's biosphere, right?
Yeah.
And then resistivity.
Yeah. No, mine doesn't. How about was there bad work? There's that heavy duty.
I have a question.
Yeah, questions?
Yeah, it was this one. Reading the textbooks, and there's like a lot of questions.
Yeah.
We didn't talk about.
I guess, there was this place.
Oh, yeah, I mentioned that in my later class, I didn't tell you guys. So the other thing we can do is you can redefine the permittivity. So epsilon naught is permittivity of free space. So when you put in a dielectric, kappa times permittivity, which we define as an arm. So that's what epsilon is. So epsilon is just kappa times.
Okay, and then there was also something called an Emacs of like like each. So this time about
The dielectric.
yeah, the own kappa and its own Emacs, which is like the amount of charge.
Right, so that's the breakdown. That's right. So that's when. Which is the same. Yeah. So they're just doing it more of a. That expression is more of a mathematical expression. Where when I wrote down, it's more of the actual meaning of it. But they're both the same. So that's epsilon is literally just kappa times epsilon. Which means that that's actually upside down. So this should be epsilon over epsilon.
But it's like,
Yeah, because epsilon is equal to kappa times epsilon. So if I multiply it over here, you're saying that epsilon naught is equal to kappa. So it should be. So epsilon is kappa times epsilon, which means kappa is then epsilon divided by epsilon. Okay, so just. What's up, person?
So what is it spelled outfit then?
Yeah,
Is
we
it-
have to do this.
So alpha is just an alpha particle, so this is, the only thing you really care about is two things, the mass of it, which gives you the mass of the bottom, and the charge of it, and the charge of it. So just think of alpha as just some charge. So we want units to call it Q like fine, where Q just happens to be twice. So to be, so an alpha particle is actually just two protons. So basically, it is a helium atom without the nucleus, or without the. So that's fundamentally. All right, so Wednesday, we'll start talking about what happens if you have more than one battery. How can we deal with anything with more than one battery?
Maybe I'm not on it. Yeah. I was gonna say, you haven't got the.
Some of it. So I'm kind of